Hello everyone, this is TAMUK Team 6's NASA TSGC Design Challenge presentation of our Origami Folding Solar Array project. This is the team's first semester conducting the project. Today, we will start the presentation with an introduction of the team, followed by the project background, scope, design requirements and constraints, and design considerations. We will then finish the presentation with the group's next steps and conclusion.
Hello, my name is Ricardo Cuellar. I am a senior mechanical engineering student.
Hello, my name is Leslie Carrion and I am a senior mechanical engineering student.
Hello, my name is Aaron Rocha and I'm a senior mechanical engineering student.
Hi, my name is Jonah Cross and I'm a senior mechanical engineering student.
Hello, my name is Mauricio Fernandez and I am a senior mechanical engineering student.
Hi, my name is David Balderas and I am a senior mechanical engineering student. We all attend Texas A&M University, Kingsville. We will begin this presentation with some background on the project. A solar array is an assembly of solar panels used to facilitate the conversion of sunlight into electricity. Solar arrays are often used on space vehicles since there is no other easily accessible power source in space besides sunlight. Origami is a traditional Japanese paper folding technique most commonly known for creating intricate moving designs. Recently, this paper folding technique has found its way into many engineering applications, including robotics, medical devices, policing equipment, and much more. This is because origami offers a great deal of unique advantages to your engineered design, specifically the ability to collapse large structures into compact volumes. One application that sees significant potential for the implementation of origami engineering is the use of large space solar arrays. As the importance of space exploration increases, larger and more powerful spacecraft will be required for longer space missions, which will in turn require a large solar array to meet these power requirements. This can be an issue if the expanded surface area of the solar array is significantly larger than the size of current-day launch vehicles, because then the solar array will not be able to fit inside the payload bay. Our proposal is to design and prototype a solar array for a large spacecraft that uses origami folding techniques to help retract the structure into a compact volume that fits inside the payload bay of a commercially available rocket. A few of the performance indicators to help gauge the success of our design will be the solar array's packing factor and overall weight. We must design a solar array with a large expanded diameter to retracted diameter ratio and a large expanded surface area to packed volume ratio, while ensuring the complexity of the design does not significantly add to the weight. This will help determine the effectiveness of the use of origami folding techniques compared to other less complicated retraction and expansion methods. Aspects not included in the scope of this project will be the implementation of a solar tracking mechanism and the electrical engineering concepts involved with the electronics and wiring of the solar panels.
Hi, my name is Jonah Cross and I'll be discussing design requirements for the origami solar panel. The expected lifespan is 30 years with an energy output of 150 kilowatts. Due to the extreme conditions in space, our solar array will need to be immune to ultraviolet rays, or UV, and atomic oxygen, or AO. It will also need to withstand impacts from micrometeors in the plasma field, as well as temperature cycling that ranges from negative 250 degrees Fahrenheit to 250 degrees Fahrenheit. Our goal is to have the solar array weigh less than 4,800 pounds. When folded, the solar array will need to fit into the payload area of the SpaceX Falcon with a diameter of 17 feet and a height of 43 feet.
We are considering two different folding patterns for our design. The first is the accordion folding pattern that is currently used on the ISS. The advantage for this one is that it is less likely for damage to occur during transport and deployment. And the other one is the flasher folding pattern that we are leaning towards because it has about 10 times increase of deployable diameter to folded diameter. And by adding fold lines along other axles, we expect to maximize the stored volume space within the transport vehicle.
On the left, we have an example of the hexagonal flasher model being expanded and retracted, and on the right side, we have a square flasher design model being expanded and retracted.
For our mathematical model, we will be using a Mathematica 12 notebook that sets up the constraints for a general flasher and solves for the vertical coordinates for both the crease pattern and the folded form, the total surface area, and the folded volume. So for the inputs, M is the number of sides in the central polygon the pattern will wrap around, and you can see that on the top right picture. H is the number of axial bends between the bottom and the top of the folded cylinder. You can see that at the bottom right picture. Capital H is the height of the packed membrane, and we find this with the formula H is equal to lowercase h over square root of 3L, with L being the side length of the polygon the member folds into. R is the number of rings in the pattern that you can see on the bottom left picture, and delta is the specified spacing between vertices.
On the left is a CAD model of a segment of a flasher origami fold, and on the right is a CAD model showing a conceptual folding of this origami fold.
I'll be going over the kinematic structure and how these two self-deploy methods, the motor-driven truss method and the scissor method, work. So the motor-driven truss method, this method uses springs and a motorized truss to deploy the array open. At its initial state, the springs are then released, causing deflection to self-open the array, then having the motor fully unravel the array. As goes for the scissor method, the scissor method uses a shape memory polymer and rotational pins and rotational hub to operate.
After considering other actuators used in similar projects, we have decided to move forward with an electrically powered actuator. Once we determine the kinematic structure for the solar array, we can determine if this electrically powered actuator should be a motor or a linear actuator. Here on the slide are some pros and cons for a motor actuator.
The thickness of the solar panels used in this folding mechanism is very important because the thickness will impact the solar array's ability to fold into a compact structure, and it will also determine the gap that is needed between the panels so that way the mechanism can fold properly. The overall thickness of the solar panel is determined by the panel substrate, the solar cells, the glass, the encapsulant, along with the other layers that make up the solar panels themselves. After contacting SpectroLab, we found out that the substrate is completely customizable and can be customer defined, so that way it meets the desired design specifications. Pumpkin Space Systems told us the same thing, however they were able to provide a general thickness for each of the layers that make up a solar panel. An overall solar panel thickness will be established after discussing our project further with the solar panel manufacturer. As to the solar cells, we're considering 3 of SpectroLab solar cells. However, we would more than likely use the XTJ since it has a higher efficiency and higher power output.
Origami is usually performed on paper, which is considered a zero thickness model, but our structure has a finite thickness. We have compiled our top 3 options when it comes to thickness accommodation methods for folding. The first method, the offset panel method, utilizes the zero thickness plane and is kinematically equivalent to the original origami pattern. This means that the offset panel design folds in the same plane as the zero thickness model would. The downside to this method is that there are high stresses on the joints due to the offset distance. Next, the double hinge method allows for great movement throughout the entirety of the folding process. On the other hand, the panels need to be shaved down around the edges to prevent interference from folding and unfolding. Finally, the membrane method was the most common method found in the literature. It requires a thin flexible membrane under the solar panels to serve as the flexible joints for the array. This method has excellent flexibility, but constant tension at the edges of the structure is needed to keep it in the deployed state. Also, this method does not guarantee consistent motion, which has to be taken into consideration when a deployment method is selected. In the next slide, there are some animations that we created to simulate the motion of each thickness accommodation method.
Our next steps include finalizing and establishing external loads and other constraints. We will also establish the thickness accommodation technique that we will use for our mechanism. We will determine the solar panel thickness and begin a mathematical model for the designs that are being considered. From those results, we will be able to perform a down selection of the folding patterns and decide which one is the best for our application. From there, we will choose our actuator and deployment mechanism that best suits our design. Then we will finally initiate a CAD model and analysis and then begin our scaled prototype.